We're going to look at hash tables, and we're going to explore how we can use them to help us search quickly for data that are stored within those tables. Now, hash tables are data structures that contain key and value pairs, much like dictionaries. Hash tables allow data to be stored, to be accessed very quickly without the need to search through every record. If we think of some other algorithms that we're aware of, like for example linear search, we have to search through every record to find the value that we want. Even for binary search, we still have to do some kind of searching. We have to order the data beforehand. We still have to do searching again to find the value we want. But with hash tables, we can get straight to the value that we are looking for. So it's a much quicker way of accessing the data that we're after. The way it does this is by having a key that allows us to calculate the index position of where the value is stored. So we're going to look at that now by way of a couple of examples. So in this worked example, I'm going to have it so that we use the value as the key. So we don't have a key and value pairs, we have the value is the key. So the index position of the item in the table is determined by assigning a key that is based on its value of the item that we wish to store. Now this doesn't have any practical application, but it helps us to understand the principle of how the data are stored and where we store the data in the table. So to begin with then, we're going to put these numbers into a hash table, and we need to create the table. Now the table itself needs to have a length or number of bins that is larger than the elements we have. So you can see there we have 6 elements. So we're going to create a table that has 10 elements. It really makes it simple for us to do that. As you'll see in a minute, we have 10 elements in our table. So this is our hash table. So it's completely empty at the moment. So what we'll do now is slowly add the values to our table, but we need to understand where those values in the table are going to go. So we are going to put those values in the table in the index position based on the values that they are. But because the values are bigger than the length of the list, we need to apply a modulo to the number of the number of bins to the value. So we're going to demonstrate how we do that now. So let's take the first value in the list, 81. We're going to apply the modulus of 10. The reason why we do 10 is because our hash table is 10 elements long, so it has 10 bins. We apply that and it gives us a remainder of 1. So what we're going to do now, the value 81 is going to go into index position 1. The next value is 93. So again, we apply modulus 10 to that, and that will give us a value of 3. So we put the value 93 in index position 3. With 76, again, when we work all that out, we put that value into index position 6. Now, with the 51, when we apply modulo 10 to that, it gives us a remainder of 1. Now, we already have a value in that bin. So this means that a collision has occurred because that bin is already occupied. So in this situation, the data then are going to be placed in the next available bin in the algorithm we're using here to the right. So we're going to place it now in element 2. So 51 now goes into index position 2. Next value there is 17, which gives us a remainder of 7. So we put that in index position 7. And then the final value, 61. Again, we have another collision. So we put this again in the next available position on the right. So we can't put it into 2 because it's already occupied by 51. We can't put it into 3, it's already occupied by 93. So we're going to put it into index position 4. So we've demonstrated there how we put our values into our hash table and where we put those values. Now we're going to explain how we do it in the context of a phone number where we actually have the key and the value pairs. So in that previous example, didn't really have a practical application, but it's just demonstrating how we place the values in the right index position. Now we are going to take our key value pairs. So in this scenario, we have the key, which is the name of a person, and the corresponding value, which is the phone number. So if we think about how this works, we know the names of our friends, of course, but we don't necessarily know their phone numbers. So it's easy for us to take the key and to remember the key as opposed to remembering the value. So we are now going to demonstrate how the hash table works in this context. So if you imagine that we have our key name value, so in this example here we have 5 names with corresponding phone number in our contacts list, 5 elements, but we're still going to use a hash table with 10 elements. It makes it much easier to do our calculations. So we're just going to stick with a hash table of 10 elements here, so that should be fine as long as we have more elements than we have values we want to put in. Now in this case, because our key is made up of letters and not numbers, we need to convert those numbers to ASCII to convert them into numbers. So we'll do that. So we take the first name there, which is Homer, find the corresponding ASCII values of those, and we add them up, which gives us 507. We take 507 and apply mod 10. Remember, we've got 10 bins, so we do mod 10. And that gives us a remainder of 7. So what we do then in bin 7, in index position 7, we put in both the key value, both the key and the value. So we put both those things in there, the key and the value itself. So we do that for each of our people in our contacts list. So we do that for Bart, Lisa, Milhouse and Ralph. Now look at Lisa's one here. This is interesting because we have a collision at this point. So we can't put it in index position 3, but the closest one to index position 3 that's empty is position 4. So we put it there. Now that's all and well putting the data in. Well, how then do we retrieve it? Well, we retrieve it in the same way as we put the data in. So supposing we are looking to find the phone number of Bart. So what we do is we calculate everything again as we do, take the ASCII values, add them all up, apply the modulus operator, which gives us position 3, index position 3. We know in that position that's where Bart's number is kept, so we go in there and we see that it's Bart with the corresponding phone number. So we know that the key, which we know Bart, but the phone number value, which we don't know necessarily, so we can access both those values. Now it gets a bit trickier with Lisa, so we do exactly the same thing. We take all the ASCII values of each of the letters, add them up, apply the modulus operator, gives us index position 3. But at this point we check, and this is why we need to store the key. We check the key, which is Lisa, against the key Bart, and we see that they're different. So we know that the value, the phone number for Lisa, the value for Lisa that we're after is not stored in index position 3. So we need to, again, understand that the value would be most likely stored in the next available bin, in this case to the right. And we then look in that index position 4, and we see then, we compare the key Lisa with the key that's in there, which is Lisa, and we know they're the same, and then we're able to extract the phone number. So we're able to pull out phone numbers really quickly, and even when we have a collision, it's still much faster than, let's say, linear search to find our item in a list. Now you may find that if you get lots and lots of collisions, it may be necessary to rehash with a high modulus. You may need to increase the number of bins. So this is what we call rehashing. Now, ideally, you want to have a load factor. So the load factor is the number of occupied bins divided by the number of total bins. So essentially, if 5 bins are occupied, then the load factor is 0.5. Now, you want to keep load factor low, but obviously there's an efficiency in terms of memory storage. Now, ideally, you want to have as few collisions as possible, but it may be necessary to have empty bins to ensure that you're minimizing the number of collisions. So the hash table should contain more bins than the elements, of course, by a load factor of 0.75. But that's the general rule of thumb. You may have to modify things around that, but as a general rule of thumb, that should minimize the number of collisions without having excessive number of empty bins. That's the sort of balancing act we're trying to achieve there. The key needs to be stored in the table, as we talked about, along with a value for the reason that we might have collisions.